Welcome, everyone. Thank you for joining us for today's webinar, What to Know About Hazard Containment Solutions, presented by Matt Edel. BakerRisk has decades of experience completing incident investigations, loss prevention studies, testing and research, and risk management services. We are excited to discover how expertly designed barricades and solutions, such as BakerRisk shock and fragment enclosure, is proven to mitigate hazards. Now, for today's webinar, I want to go over a few housekeeping items. First, we have posted links in the chat to content related to our webinar subject. We invite you to explore BakerRisk's published papers, previous webinars, and BakerRisk Training Center courses. Second, we want to respond to your questions following this webinar. Please type questions into the Q&A box in the Zoom control panel, and our presenters will respond to the questions. Finally, at the close of our webinar today, please provide feedback by responding to our survey. And now for the webinar. This presentation will focus on some common types of hazards that may be considered for containment and typical ways that they are mitigated. BakerRisk presenter Matt Edel is a senior principal engineer at the San Antonio, Texas BakerRisk office. He has leveraged over 20 years of experience performing high-pressure tests to better understand high-pressure hazards, designing and analyzing mitigation solutions such as enclosures and barricades, and supporting relevant codes and standards. We're excited to have Matt to present this afternoon, so without further ado, I will turn the time over to Matt.
Thanks for the introduction. I'm happy to be able to present today on what to know about hazard containment solutions. As we get started, I'll start with a brief overview of what today's webinar will be about. There's three main points that I'll be covering. The first will be notable losses. In other words, some accidents or other types of unplanned releases that have occurred in industry. I'll follow that up with a brief review of relevant and pertinent codes and standards that are out there as they pertain to the different industries of concern. And lastly, the bulk of it will be the third one, which is to cover some different options that are commonly considered for mitigation of these types of hazards. Okay, so first, some notable losses. I want to start this section with a brief overview of the types of hazards that will be discussed today. Those are shown in the table here. The first one is an application of pressure testing or vessels, piping, or equipment that are under high pressure of different types of fluids. Some of the common hazards considered for those are projectiles that could be thrown in an accidental burst or other type of failure, blast loads from a sudden release of high pressure gas, or liquid jetting. Industries that this is of common concern to are listed on the far right. This is places like in oil field services, space and space exploration, and the growing hydrogen industry has these concerns as well. The next type of application is batteries, specifically with battery abuse testing and lithium-ion battery failures. Hazards obviously are when things go wrong and the battery can catch on fire or have an accidental explosion. These types of industries are in the automotive industry, battery energy storage systems or BESS, as well as battery manufacturers are concerned about this. Third one is rotating equipment. This covers a lot of different industries, specifically in manufacturing and heavy industry, as well as different types of engines. Main type of hazard with this would be what they call a blade off situation, when a blade from a high-speed rotating equipment accidentally fails or comes apart and then gets thrown at pretty high speeds. And then the fourth and last is explosive storage or handling. Obviously, the hazard with this would be an explosion. Different industries would be the military, Department of Defense. Again, with space, they often have different types of explosives that they have to handle or store at their facilities. And of course, explosives manufacturing. Specifically, applications that will not be covered today are shown in the bottom there, would be toxics and spills. Want to show a few different types of examples. This first one is a large field assembly of a large pipe failure. This incident occurred just a few years ago in September of 2018. It was a hydrostatic test, in other words, with liquid out in the open. Here you see the burst just occurred. It was recorded, I believe, by somebody's personal cell phone. It's an unknown location, but based on the video and audio, I believe it was somewhere in the US. And the pipe wall failed suddenly and catastrophically. You see a still image there of the pipe as it burst. Had a sudden release of high pressure liquid. There were no injuries that were recorded as part of this. So nobody was hurt, fortunately, due to people being a pretty good distance away, but they very well could have if they were up right on top of the equipment at the time of the incident. A couple of types of hazards from this type of an accident are projectiles that could be thrown. In this case, it just split open, and I don't believe there were significant projectiles, or liquid jetting, which definitely did occur. The next incident that occurred that I'll go over happened in the aerospace industry. This one happened in Italy back in December of 2021, less than 2 years ago. You see here, that's a concrete wall that had a pretty good sized hole punched through it. And that's a door through which this very large projectile got thrown. This was also pressure testing of a pretty large vessel or piece of equipment. There were no injuries that occurred, but there was significant infrastructure damage. In addition to what you see in the video, there was an overhead crane inside the building that fell. Some of the doors were torn off. And again, the reinforced concrete wall was perforated. Next one I'll show, and I'll warn you, this has some sensitive material in it. This was at a flow control valve, and you see the incident just occurred there. This one occurred less than a year ago, December of last year. It was a manufacturer of a pressure control valve for pipeline control in India. And while they were filling this large vessel with air, the wall or flange burst, and the cover got thrown at a very high speed. And unfortunately, it impacted an operator, and the person was killed. A pretty thorough investigation was done afterwards, but you can see it's done in a fairly crowded or heavily occupied room. So there's lots of people very close in to where this different types of equipment is under pressure. I think one of the images coming up here, that's the item that failed, where it was thrown off. That's the column where the flange impacted nearby the operator. This next one occurred in August of 2020. This was in upstate New York in the US. It was a high pressure food processor, a piece of equipment that failed when they were conducting a pressure test. It was a catastrophic failure of a pressure vessel, and unfortunately it injured 2 people and killed 1 person. Notably, the person who was deceased from this accident was a former mayor of the town where it occurred. He's also a notable contributor to the ASME pressure vessel code. So those were a few accidental releases of high pressure, such as vessels or equipment. The next few that I'll go through are from battery storage units. This first one just occurred last month in September of this year near San Diego, California. It was a battery storage unit fire. There was a thermal runaway event in a lithium ion battery. There were no injuries reported, but it did result in fairly significant mass evacuations nearby, as the gas from the fire that burned was thought to be potentially toxic. Next one is similarly another battery storage unit accident that occurred. This was in September of last year, also in California, but Northern California near Monterey. This was another fire that occurred in a battery storage unit. Again, there were no injuries reported, but this one was fairly significant. It impacted the nearby community, resulted in the shutdown of a major highway that was nearby for about 12 hours. And this next one, another battery storage unit that occurred. I'll play the video for this. This one occurred in Taiwan just this past summer, actually on July 4th of 2023. Nobody was, there were no casualties from this, but it resulted in a total loss of the battery energy storage system, or BESS. This was a lithium iron phosphorus cell. And you see a quote here: "The fire department did not dare to be careless. Opening the container door rashly was thought to cause instant backfire or deflagration." In other words, they didn't want to open the door during firefighting. They were worried that would introduce oxygen, causing even more spread of the fire. You see that image there. The whole battery system was a total loss. Quite a few images here of the different damage. I'll let play out for a little bit. Next, I'll shift gears a little bit and talk about rotating equipment. These first two obviously makes the news anytime there's some type of failure in the airline industry. The first one on the left was Southwest Airlines pretty recently, back in April of 2018. This was a failure of one of the engine blades. It was thought due to metal fatigue. That fatigue resulted in a crack that grew, and once the crack grew big enough, well, then the blade totally got thrown off. And then the one on the right was Delta Airlines a little while ago, back in July of 1996. This was found to be a manufacturing fault of the engine blade to cause a crack in it, and it eventually got thrown as well. One more failure that occurred in the rotating equipment industry is shown here. This is a turbine engine failure at a power plant. This occurred in November of 2011 in Minnesota. The turbine engine was a failure at a coal-fired power plant. This was found to be due to stress corrosion cracking, and that caused a crack that grew and one of the blades was thrown. There were no injuries from this incident, but it resulted in very significant infrastructure damage and repairs, totaling about $146 million in both repairs and business interruption. And then lastly, I wanted to show more of a demonstration. This was not an accident occurred. This was done at BakerRisk test facility. This is to show an example of what we would consider an improperly designed enclosure. This has a pressure vessel inside the box here. The vessel is shown in the image on the left. It's approximately 4-inch diameter by 60-inch long. The test was conducted using high-pressure nitrogen gas at over 26,000 psi. I'll let this play here. You'll see once the release happens, there's rippling of the panels on the sidewall, and there was a release of a bull plug on the end that got thrown toward the left of the screen. Again, it was by design shown to be a demonstration of what could happen with it. Although you may have an enclosure that provides line of sight protection, if it's not designed properly, it's going to come apart, and you see there's fairly substantial secondary debris from the different components of the enclosure that are getting thrown as well. So that concludes the first part of notable losses. The second part, I'll go into some of the pertinent codes and standards for a few of the different industries that we're looking at here. First few are shown here for the battery industry. I won't read through every one of them, but some of the more significant ones are listed here from NFPA, Technical Committee on Energy Storage Systems, and UL, Underwriters Laboratory. There's a few different ones specifically for lithium-ion batteries. It also goes through some standards, I believe, on how to conduct battery abuse testing. It's done in a lab environment before batteries are approved for release and use. There's also some pertinent standards from the high pressure testing industry. This first one is from ASME. It's called Repair of Pressure Equipment and Piping. The reference code is PCC2. This covers pneumatic testing, which is with the gas. And it says that if the risk from potential projectiles or blast loads is too high, then you need to use a safe standoff distance or some type of barricade. But unfortunately, at this time, it does not provide any guidance on how to go about designing a barricade. It just says that one would need to be used for hazard mitigation. And then for hydrostatic testing with a liquid, it does not offer any requirement or even recommendation for mitigation of hazardous risks. Another code or standard pertinent to the high pressure industry is published from the UK's Health and Safety Executive, or HSE. It's called GS4, or Guidance Note 4. The title is Safety Requirements for Pressure Testing. This one does go into a little bit more detail in that it requires physical separation between the operator and the items under pressure, either using adequate separation distance, or what we would term safe standoff distance, or the use of barricades or enclosures. It further goes on to say that if an enclosure or barricade is used, then it must be designed for blast and projectiles. It does provide a few methodologies in a reference document for how to quantify the hazards and design barricades, but it's found to be fairly conservative. What it does is it converts the stored energy of the pressure system to equivalent weight of high explosive in terms of TNT. And that tends to provide an overestimate of the peak pressure from a blast load. And then one more standard from the high pressure industry is specific to the growing hydrogen industry. This one is NFPA standard number 2, Hydrogen Technologies Code. I'm specifically referencing the 2016 edition here. That was the first time that they introduced some requirements for performance-based mitigation for both explosion and fire hazards through use of containment enclosures. I believe that's been carried through in subsequent editions of NFPA 2 as well. And then the last standard that I'll cover is in terms of rotating equipment. OSHA has a few different standards covering this area. A couple of them are mentioned here: 1910.212 and 1917.151. It covers what it calls machine guarding. Basically, this addresses making sure that personnel hands are away from rotating machinery. It does mention barricades or enclosures to contain projectiles, but it's more from hazards associated with mechanical motion, what it terms chips and sparks. But unfortunately, these standards, what we found, do not cover protection from projectiles in case part of the rotating equipment itself were to fail or come apart. So the third and last part of the presentation I'll be covering today is on mitigation options. First, a brief overview of some of the different options is shown here. The first one on the left is a safe standoff distance. This image was taken from a YouTube video online of a BLEVE, a boiling liquid expanding vapor explosion of a vessel that blew up, and then had blast loads from the sudden release of high pressure gas. So with the standoff, you can have what's shown here in the dashed yellow line. It's basically coming up with a calculation to determine how far people, or in some cases infrastructure, would need to be far enough away so that they don't get hurt or that infrastructure is not significantly damaged. And then the second main mitigation option that I'll cover is through a barricade or enclosure. You see this top image on the right. This is just stacked concrete bin blocks that may be suitable as a barricade wall for certain applications. One type of a barricade or enclosure that I'll cover is what I call stick built. This is something that's more conventional type of construction that's built in place. And then the other type that I'll go through lastly is a safe enclosure. Shock and fragment enclosure is what SAFE stands for, that BakerRisk offers. Okay, so the first mitigation option is a safe standoff distance. This is covered in ASME's PCC2 document for high pressure testing. It provides standoffs separately for both protection from projectiles and from blast loads. What it does is it gives a projectile distance based on how far it might be thrown as a trajectory analysis of a primary fragment. It also provides blast load distance requirements for injuries to people and for damage to buildings. Both of these approaches are based on equivalent TNT explosions or high explosives. So again, as mentioned previously, this approach we have found to be significantly conservative for quantifying hazards from high pressure testing. One advantage of using a safe distance is that obviously it's a low cost. You don't have to actually build anything. You just have to ensure that people are sited far enough away. So there's no construction. But a couple disadvantages. First and foremost, typically this would be associated with a fairly significant standoff distance. So it's going to require a good amount of real estate. And a lot of the different industries that we're covering today, that sometimes is not feasible. Doing so would impede operations by having to keep people far enough away when something is under high pressure. The next type of mitigation to be covered is stick built in terms of a barricade or enclosure. This can be conventional construction, usually, such as reinforced concrete or structural steel or something similar. It can be custom designed. However, a word of caution, it's noted here, that last bullet, the designer must be experienced with designing for projectile impacts and blast loads. So some advantages and disadvantages are shown in the table here. First advantage, it can use conventional materials, can also use local contractors. Sometimes that's important or even required, particularly if it's done in an area with labor unions. Another advantage, it does not require large standoff distances because you're essentially containing the hazards. And lastly, an advantage is that it accommodates the available space that it gets put in a factory or manufacturing plant once it's built and constructed and open for operation. There are, however, a few disadvantages. The first is it's associated with a fairly long construction schedule most of the time. Can also be intrusive. It's messy business also throughout the process until it's done and in place. It can also be relatively expensive. And lastly, it requires a fairly significant amount of time from one of the site personnel who has to manage the project, oversee the different contractors, coordinate schedules sometimes from different trades and things like that. A lot of times that means taking someone away from their regular job and assigning them to be a project manager throughout the construction process. I have a couple examples here of conventional enclosures in these next couple of slides. This first one is a single standalone enclosure. It's constructed of reinforced masonry walls. It has a concrete roof. There's a structural steel door. And one feature you can see here, it has this monorail sticking out through the door to make it easier to pick up the item that's going to be brought into the enclosure for testing, and then again they can use the crane and monorail to take it back out. Okay. Another example is shown here. This one is a cast in place reinforced concrete, more of a bunker style, if you will, has reinforced concrete walls and roof, very heavy duty, very stout. This example has multiple bays. One other point to be made for conventional enclosures, this may be particularly desirable when you're building a new facility from scratch. I mentioned it can be messy and intrusive. Well, that's obviously not a concern if you're doing it in the first place before a facility is open for business. And then the last type of mitigation option I'll go through is a safe enclosure. SAFE stands for shock and fragment enclosure. This is an offering from BakerRisk that has several different features and advantages shown here. This is essentially a turnkey approach where BakerRisk would design an enclosure, construct it, usually prefabricated off-site, deliver it to site, and perform any final installation. An advantage is it has a single point of contact for all activities, so it removes the burden of project management from the facility, and BakerRisk takes that role. One advantage, it does not use local labor for the construction. Another feature is it's all prefabricated off-site. That brings an obvious advantage that it's not disruptive during the construction process. All that's done off-site, it's delivered to site, and it's a very minimal amount of time and certainly not a whole lot of mess during the installation process. One disadvantage is there can be size and weight limitations for transportation. As this is done off-site, obviously transportation is a key aspect of bringing it into being. The third feature is we can offer custom designs with this. These can also accommodate available space, just like a stick-built option. And it also it removes the requirement for large standoffs if it were done in the open, for if you were trying to mitigate just with a safe standoff distance. One disadvantage with this is it does introduce a barricade or enclosure, so the operations is going to have to get around that. And then lastly, a feature is it can use a variety of materials. We've offered safe enclosures using things such as concrete, steel, ballistic blankets, Lexan panels, and others, just to name a few. So it's not a one-size-fits-all. It can all be custom for the specific application being considered, but a disadvantage, it's not going to use local materials. One thing of note, all shock and fragment enclosures from BakerRisk are designed using methods that have been validated, and they've all been custom designed for the specific hazard at hand. Typically, if there's a blast load hazard, BakerRisk will model that with a CFD model shown on the left. And you can see as marching through different times, this is an example of a sudden release of high pressure gas in an enclosure. And so we'll get blast loads on different surfaces of the enclosure and then use that for a structural design using something like could be a simplified single degree of freedom or SDOF model. That's shown in this image at the bottom. That's an equivalent spring mass system, allowing for dynamic nonlinear structural analysis. Or if something more sophisticated is needed, we can use a finite element analysis or FEA model for both a projectile impact and for blast response. And lastly, BakerRisk will also analyze the specific projectile hazard using methods that have been developed in-house as well. We validated our design methods through testing. I have a couple example test videos to show. This first one on the left was a sudden release of high pressure liquid. This was done at elevated temperature. So you can see it's a vessel on the left, insulation wrapped around it. And it'll fire a projectile off toward the right to a target. So this is one example. Although it's liquid, the high temperature does make the liquid flash to steam when it gets suddenly released into the atmosphere. And in doing so, it has a higher amount of stored energy. It also introduces a blast wave as that water flashes to steam. One more example is shown on the right here. This is an example of a release of high pressure gas using nitrogen. You see a projectile that is launched toward a concrete target. And you see here in this example, there's actually back-face spalling. In other words, a chunk of concrete gets thrown off the non-loaded face of the concrete wall. So that's something that obviously BakerRisk would consider and design for this type of application to prevent that, as you don't want to have some of that as secondary debris hazard that could potentially injure someone or damage infrastructure. Have a few examples to show of some recent safe enclosures that BakerRisk has commissioned. First one is an example of a 7-foot cube. This is prefabricated steel. It could be any size. Again, it's just one example. This image on the left shows a view from the front with the door. Has some very heavy-duty door latches that an operator can easily slide open and close. And then the image on the right shows the same enclosure with a view from the back. If you look close there, you see some items here on this back wall. These are openings that are cut to allow for utility penetration, such as a high pressure tubing, electrical, and otherwise. So we'll put typically for this, we'll put a bulkhead plate over the cut opening, and then they can cut holes through the bulkhead plate as needed. It also has a flange on the back for draining liquid from a hydrostatic test. Same enclosure is shown here. This left one is a view from above, from the roof. Obviously, we've got pad eyes here so that it allows for lifting with slings and a crane. It has some flanges on the roof as well for duct exhaust. Could also be done for bringing in fresh air as needed. And then on the right, we've got the enclosure with the door opened. You can see it's just a decent, modest-sized room. For this one, we had lights installed beforehand as well. And then those bulkhead plates that I mentioned are shown here installed from the interior surface of that back wall. The next enclosure is another booth enclosure. Although the first one was for a high-pressure application, this one was for battery abuse testing. So a very comparable size, 8 foot instead of 7 in terms of width and length, also with structural steel. But again, you can see a very similar type of design approach. This one had a bulkhead opening on a sidewall. You see a pretty big size opening here on the right photo. That's for installation of a damper, as bringing in fresh air was crucial for the operations during the battery abuse testing. And then off in the distance here, you can see a second one that was being built. These gray panels are vent panels. So this one was designed so in case of an explosion from battery abuse testing, the blast loads would vent out those panels, they open up, and the loads would go outside. More on that here in this slide, but first, just to show some of the process, you see these enclosures were lifted with a crane, put on a truck for delivery, offloaded with another crane at site, and then brought into final position here. And I mentioned those vent panels along the back wall that would open up into this opening in the back wall of the facility to vent out to the atmosphere. And then once this was brought into site, BakerRisk and our team oversaw final installation. That included installation of concrete anchors into the floor slab. So those are both examples of booths. This next one is what we call a horizontal bunker. I'll let this video play. It shows an animation of a different style. This one is a little bit smaller. They typically run about 3 to 4 foot tall by 3 to 4 foot wide. This one here initially is 10 foot long. It's made of prefabricated structural steel. There's a hinge lid that can be opened and closed. You saw a bar on the back wall that was a counterweight to make it so that an operator can easily open and close it. You can see it can be adapted to be any length that's needed. Here we're bringing in more middle segments. Here's one on the left. It'll bring in another on the right. So for this example, we go from 10 foot to a total of 30 foot long. And then the two end walls are quite a bit stronger. This one is ideal for something like a long horizontal vessel with a significant on-axis type of a hazard, such as in the oil field services industry. They might test a long tubular that has a bull plug or an end cap. And if those get accidentally thrown, well, they're fairly significant, so that substantial end wall is designed to withstand that type of an impact. Here's some photos of an example that's been built. This one on the left, it's a little bit hard to see, but it's a view from the end. In the foreground are all the controls for the operator to use. This one, the lid is in the open position, and the operator would bring in the long tubular from overhead using a crane and drop it into the enclosure for testing. This image in the middle, same thing, it's just a view from the side. It shows a lot of the hardware. There's some very strong latches that are used to secure the lid once it's in the closed position. And then lastly, the image on the right is a view from the backside. This has hydraulics that are used to open and close the lid. It has some very heavy duty hinges and hardware to make sure that the lid can withstand an impact and not get thrown itself as well. Lastly, for the horizontal bunker, BakerRisk has validated the design and effectiveness. This is a short video here of a test done hydrostatic, so it's with liquid, at 17,000 psi, and it was intentionally done to throw a projectile on axis that weighed over 100 pounds. Let the video play here. You see the enclosure moved a little bit to the left initially. I'll play it again. That was from the 100-pound plus projectile impacting the left end wall, and then the whole enclosure moved suddenly back to the right. Well, that's from when the body of the vessel went in the opposite direction and kicked it back as it impacted the right end wall. Here, I'll play it one more time. Another type of safe enclosure shown here. This is a pressure test cart. Again, it's designed for sudden release of high pressure fluid. This one obviously is fairly small. The item is placed inside the cart for testing. One feature is that it's mobile. Obviously, we're using Lexan panels here, so the operator is able to witness the item under pressure. So this is just an example. They don't all have to be bunkers. They don't all have to be big boxes. They're all custom designed, again, for this specific application at hand. And they don't have to actually be solid panels or rigid panels. This is an example where a pressure vessel was wrapped with a ballistic blanket. The vessel was in a unit at a chemical processing facility in operation. They could not take it down to install protection, but they had identified there was unacceptable risk of a failure of the vessel. Specifically, they were concerned about projectiles that could be thrown from the event of a vessel failure. So the mitigation option that was selected was to wrap it with a ballistic blanket. This was custom designed and manufactured to envelop it. It was wrapped around the circumference of the vessel. Here's one more type of example. This one we call a walk-in room. There's an animation video here that I'll play to show it. We'll start with a single, what we call single wide pressure test enclosure. Again, one of the challenges with prefabricated is transportation. It's got to be able to be fit on a truck. So this is essentially the size of a standard shipping container. It has a crane rail that can be used to bring the test item into the room. It has an elevated floor that's designed as a catch basin to test liquids from a hydrostatic test. Once you're done with the test and the liquids come out, then you can safely contain it all and then dispose of it as you need. It can also be adapted to a double wide in any length as well. Video continues here and shows converting from a single to a double. Essentially just open up the common walls. So those are being removed and it's put together and then welded or bolted in place on site. This example has the main part where testing is done in the foreground, and back behind the wall there would be a control room where the operator can use the different pieces of instrumentation to conduct the test. And lastly, a couple other types of options that could be used for safe enclosure. First one on the left, it could be made of precast concrete. This is more of a culvert style, but something like that could be easily adapted. Again, with the main features being turnkey and most of the construction done off site. Next one is the image in the middle for a test pit lid. Obviously, the test pit would have to be done more stick built on site, but you could mesh or marry that with the safe enclosure for the lid. That lid could be prefabricated off site and brought in to work with the pit in the facility. And lastly, a blast mag. This is something that uses very thick or heavy duty cabling that's woven together in a weave. Most of these blast mats come in sizes on the order of 8 foot by 8 foot. This is something that is very effective at stopping projectiles, maybe not so much for blasts. So one example could be protection from rotating equipment or from a hydrostatic pressure test that doesn't have the blast loads that a pneumatic test would. And lastly, some closing thoughts, things to consider here. First, should I use a hazard containment enclosure? I went through a few of the different standards and regulations. Some of them are somewhat stringent and more cut and dry that when they are required. There are notably some industries that regulations don't really require much or anything. But protecting people and assets is always advised. It's always a good idea. Second thought is what options are available. There's some different options that I've presented today, such as standoff distances, stick-built enclosures and barricades, and safe enclosures, and they have different associated advantages and disadvantages. Lastly, one thing to keep in mind, not all enclosures or barricades are equal. You need to ensure that enclosures are properly designed by a professional for the specific hazards of concern using industry accepted engineering methods to model both the hazards and to design for mitigation. And that's all I have today, so I'll open it up for questions.
Thank you, Matt. I'm going to go ahead and ask some questions that came up during the presentation. And just as a reminder for any of the attendees, that if you have not already done so, we ask that you type your questions into the Q&A box in your control panel. So one of the questions that came up was, what is a typical schedule for a conventional stick-built versus a prefabricated safe enclosure?
That's a good question. For stick-built, a lot of times that's done where you do the design and then the facility would shop it out for bids and then get the construction crew in line. So it's more or less done in series one after another. It can vary certainly, but a lot of times those would run on the order of 6 to 12 months. The schedule, on the other hand, for something prefabricated, like with the safe enclosure, that schedule can get condensed more on the order of, say, 3 to 6 months for a lot of common type of applications.
Thank you for that. Another question that came up is it important to protect from testing systems as well as the item being tested? For example, high pressure pumps. What is typically done for these items?
Yeah, a lot of times that's not required even in the regulations that do have some requirements, but you could very easily put a barricade or enclosure around the pump itself. Sometimes if the tubing that goes from the pump to the item under pressure, that might be exposed out in the open, you can do something like put a tether to it or put intermittent anchors to secure it to the floor or the wall so that you wouldn't get hose whipping or other types of hazards introduced.
Great. And then this will be the last question before we conclude the presentation. So are there limitations on where a prefabricated safe enclosure can be shipped and installed? Is this something that is only available in the US?
No, safe enclosures can be used really anywhere in the world. BakerRisk has a team of construction crews that help with prefabrication. A lot of that is done in the US, but they're, again, we typically overcome transportation hurdles. They can be shipped and used anywhere in the world.
That's excellent news. So thank you, Matt, for today. And if anybody has any additional questions, we ask that you reach out to Matt directly. And as a final reminder, today's webinar will be posted to the BakerRisk website. And once a recording is available, you will receive an email from BakerRisk with that link. We ask that you complete the survey at the end of the conclusion of this webinar. And thanks again for joining us today. And we will see you at our next webinar presentation, which will be Hydrogen White Paper Review in December. Thanks again, everyone. Thank you, Matt.